So complex numbers is just, yeah, really an unfortunate name. They're not really that bad. It just gives us a way to deal with square roots of negative numbers. Again, another unfortunate name, imaginary numbers. So we're going to start with a definition here. So we're going to define the square root of -1 equals I, so little lowercase I, where I is the imaginary unit. So I is an imaginary, you can think of it as a number, and one I is just like the singular of that. Okay? So we're going to use this definition in our radical strategies to simplify the square root of -4, right? So no longer is this does not exist, right? From now on, what we're going to do is we're going to rewrite that as the square root of +4, which we know, times the square root of -1, which we just defined. So the square root of +4 is 2. The square root of -1 is I. So the square root of -4 is equal to 2I. Try this next one, square root of -100. Right? So that's square root of +100 times the square root of -1. You don't have to write this step after you get used to it, but just so you can see it, square root of +100 is 10. Square root of -1, that's I. And what if it's not a perfect square? So square root of -24. Right, so I've got square root, so I'm going to look for the perfect square factors. Sure, right? So square root of 4, partner factor is 6, and then I've got the negative, so square root -1. Square root of 4 is 2. Square root of 6 is just square root 6. Square root of -1 is I. And usually what you'll see me do is I'm going to stick that I like in the front. So 2I squared roots of 6, just so it doesn't try to sneak underneath the radical. Okay, so that's our kind of imaginary number, the imaginary part of a complex number. So now what's a complex number? So a complex number looks like this, A plus B times I, where A and B, right, are just going to be numbers, real numbers. So when we add, subtract, multiply, or divide complex numbers, the result can always, mathematicians hardly ever say always be simplified to the form A plus BI. So A is called the real part, and BI is the imaginary part. And together they make a complex number. Now note, A and B can both be 0, and it's still considered a complex number. So the complex number set actually now holds all of the other number sets that you know. So it holds all the rational numbers, all the real numbers, all the irrational numbers, right? They're all contained there in that set of complex numbers. So let's go ahead and do the operations. It's very intuitive, especially for adding and subtracting. So here's one complex number, right? A plus BI. A plus BI, adding 4 minus 9I plus 3 plus 5I. So what do you think? What feels like should happen? So I'm just copying it down without those parentheses. Right, you're just going to kind of collect like terms. You're going to add the real parts with the real parts. So 3 plus 4. And add the imaginary parts with the imaginary parts. So negative 9I plus 5I is minus 4I. Right, so when you're adding and subtracting, you add and subtract real parts with real parts, imaginary parts with imaginary parts. So if I take those same numbers and I subtract, right, what do we have to be careful of? Yeah, you have to subtract both parts in the second one. So when I recopy it down this time, for that second complex number, it's going to be minus 3. And then minus 5I. And then the same thing, collect your like terms. So 4 minus 3 is 1. Negative 9I minus 5I is minus 14I. So an A plus BI, right? No extra terms. Now when we multiply, so let's take a look at multiplying. We are going to, right, what does it look like? Right? Doesn't it feel like binomial times binomial? Well, that's what we're going to do. We're going to go ahead and take, right, the 4 and multiply it through both parts in the second complex number. And then we'll take the negative 9i and multiply it by both parts of the second number. So, or FOIL, right, if you do the FOIL method. So 4 times 3 is 12 plus 4 times 5i. 4 times 5i is 20i. Then I have negative 9 times 3, I'm sorry, negative 9i times 3, so that's minus 27i. And then lastly, I have minus 45, and then I times I is I squared. So I'm going to do this in a couple of steps. So I get my 12, I get minus 7i, and then I have minus 45 I squared. Well, I said up here, when we multiply, add, subtract, multiply, or divide, the results can always be simplified to a plus bi. Well, I have a plus bi plus something I squared. How do I get rid of this term right here? I'm going to hop down here and do a little cheat. So I squared. If I is equal to the square root of negative 1, then I squared is negative 1. So anytime you see an I squared, you can replace that with a negative 1. So I have now what? 12 minus 7i minus 45 times negative 1. Negative 45 times negative 1 makes that a plus 45. So 12 minus 7i plus 45. And now those, the 12 and the 45 can combine so that I will get down to just my a plus bi. Even though my bi's keep being negative, they don't have to be. It's just kind of how it's working out this time. So what is that going to be? 57? Check my arithmetic. 57 minus 7i. Okay, 7 plus 3i quantity squared. Again, make sure you write it out and multiply and get that middle term. So 7 times 7 is 49. 7 times 3i is plus 21i. Plus 21i. And then last, plus 9i squared. 49. 21i plus 21i is plus 42i. And then plus 9i squared. So we're going to do that quicker this time. So I squared is negative 1 times 9 makes that minus 9. So to final answer, that negative 9 and the 49 in front can combine. So 40 plus 42i. Cool. Are you going to pause and try this one? Okay, so 36 minus 30i plus 30i minus 25i squared. So these are called complex conjugates. So conjugate means same terms, different sign in the middle. Complex because they've got an I in them. So right, 6 plus 5i times 6 minus 5i. I want you to notice what happens here when you multiply two conjugates. Minus 30i plus 30i, gone, minus 25i squared. So remember, I squared is negative 1 times negative 25 is going to make that plus 25. Looks like 61. No imaginary part, completely real. Okay, so when you multiply two conjugates together, the imaginary parts, they go away. So now we just have these additional powers of I. So I squared was negative 1. I cubed is I squared times I. But I squared we just found was negative 1. So negative 1 times I is negative I. So I cubed is equivalent to negative I. You should always be able to get back to either a real number or I, plus or minus I. So then let's think about I to the 4th. So I to the 4th is I squared squared is one way we could do it. I squared is -1. And if we square -1, we get +1. Okay. So notice all powers of I can always be reduced to either I, -1, -I, or 1. Okay, so for dividing, to divide two complex numbers, it's a lot like rationalizing a denominator, right, if you've done that before. So your goal is to find an equivalent expression that does not contain an I in the denominator. So our step, again, multiply top and bottom by, right, top and bottom by the same amount because we can only multiply by 1. So we're going to multiply top and bottom both by I. So let me show you how it works. So in this first one, I have 7 over I. So I want something equivalent that doesn't have an I in the bottom. So I'm going to multiply this fraction by my own fraction, I over I. So I over I is, right, a 1. And what do we get? So I get 7I for the top. Okay, fine. In the denominator, I have I times I. I've got I squared. But I squared is -1. So 7I over -1, or more simply, -7I. So now I have an expression that does not have a denominator with an I in it. Let's do this next one. So my numerator has 2 terms. Okay. My denominator only has the 1. That's great. So we're going to multiply top and bottom again by I. Let's see what happens. So the denominator, 2I squared, right, -2, good. On the top, the I does need to distribute, so go ahead and do that. So I'm going to get 5I, and then minus 9I squared. But remember, minus 9I squared is plus 9. So I'm going to have 5I plus 9. Now I said we can always write this as A plus BI. So that is kind of hiding here. I want to show you how to split it apart in case you have to put it in that way if you have an online homework system. So the A part is the real part, right? So the A part is -9/2. And the B part, the BI part, is -5/2 I. So I split it apart into 2 fractions, and each has that common denominator, but then I let the minus sign kind of float up to the top. Now this, what we had before, is totally fine, but just in case you have to get it to A plus BI. Now I want to let you know, for my dividing, I only did with a monomial denominator, 1 term in the denominator. You can do it, right? If we would have had something like the 5 minus 9I in the denominator, it's totally possible, right? I'm just not requiring my students to do it, so I'm not going to show you, but I'll tell you what, it involves conjugates, and a different way to write 1.